Hello everyone, I am Isha Kumari from Sri Venkateshwara College of Engineering, Bangalore, from the Department of Computer Science and Artificial Intelligence, and today we are going to talk on the topic real-time operating system. So, real-time operating system, the brains behind embedded systems. So the contents are as followed. Introduction to RTOs, RTOs versus traditional embedded system design, RTOs architecture, task management and RTOs, RTOs scheduling algorithm, RTOs synchronization mechanism, RTOs memory management, RTOs debugging and testing, RTOs use cases, RTOs limitations, and finally conclusion. So, what is RTO? Introduction to RTO. Real-time operating system are specialized software system designed to manage tasks, data, and resources in real-time embedded applications. Unlike general purpose operating systems, RTO is optimized for low latency, high reliability, and deterministic performance. It offers a comprehensive set of services including task management, scheduling, synchronization, memory management, and communication that makes it easier to develop complex embedded applications. RTOs is an essential component of modern embedded system design, enabling developers to create sophisticated, responsive, and reliable devices that can perform critical functions without fail. With RTOs, developers can partition their application into smaller, more manageable tasks, each with its own priority, deadline, and resource requirements. This allows them to build highly responsive and efficient systems that can handle multiple tasks simultaneously, respond quickly to external events, and meet strict timing constraints. So, RTOs versus traditional embedded system design. Traditional embedded system design involves writing code that runs on a single processor without any operating system. This approach can be limiting because it requires the developer to manage all aspects of the system, including task scheduling and resource allocation. RTOs, on the other hand, provides a multitasking environment where tasks can run concurrently. This allows for better resources and utilization and improves system responsiveness. Additionally, RTOs provide built-in mechanism for managing tasks, memory, and synchronizing, making it easier to write reliable codes. So now RTO's architecture. The architecture of an RTO can be divided into three main layers: the application layer, the kernel layer, and the hardware abstraction layer. The application layer contains the user code that interacts with the RTOs. The kernel layer provides the core functionality of the RTOs, including task scheduling, synchronization, and memory management. The hardware abstraction layer provides a standardized interface for interacting with the underlying hardware, allowing the RTOs to be used across a wide range of embedded systems. Within the kernel layer, there are several key components that work together to provide the functionality of the RTOs. These include the scheduler, which determines which tasks should be executed and when, the task control block, which stores information about each task, such as its priority and state, the memory manager, which is responsible for allocating and deallocating memory for the tasks. Task management in RTOs. In RTOs, tasks are the basic unit of work that can be scheduled by the operating system. Each task is an independent thread of execution with its own stack and context. To create a task in RTOs, you need to specify its priority, stack size, entry point, and any parameters that need to be passed to it. Once created, tasks can communicate with each other using message queues or other synchronization mechanism. So RTO scheduling algorithm. RTO scheduling algorithm are responsible for determining which tasks should be executed by the processor at any given time. There are several different scheduling algorithms used in RTOs, each with its own strengths and weaknesses. The most common scheduling algorithm in RTOs are round robin, priority based, and preemptive. Round robin scheduling is a simple algorithm that assigns a fixed amount of time to each task, while priority based scheduling assigns tasks based on their priority level. Preemptive scheduling allows higher priority tasks to interpret lower priority tasks, ensuring that critical tasks are executed first. RTO's synchronization mechanism. RTO synchronization mechanism are essential for ensuring that tasks execute in the correct order and don't interfere with each other. There are several types of synchronization mechanisms used in RTOs, including semaphores, mutexes, and message queues. Semaphores are used to signal between tasks and can be used to protect shared resources. Mutexes are similar to semaphores but provide exclusive access to a resource. Message queues allow tasks to communicate with each other by sending messages. Next is RTO's memory management. In RTO's memory management, uh, memory management is a critical component that ensures efficient use of resources. The memory available in an embedded system is limited and must be managed carefully to avoid memory leaks and other issues. To manage memory in RTOs, the system uses a combination of dynamic memory allocation and static memory allocation. Dynamic memory allocation involves allocating memory as needed during runtime. This is useful for tasks that require varying amount of memory, or for system with limited memory. Static memory allocation, on the other hand, involves allocating memory at compile time. This is useful for tasks that requires a fixed amount of memory that can help reduce memory fragmentation. And here is a diagram explaining RTO's memory allocation. So now RTOs debugging and testing. The debugging and testing process for RTOs applications involves several steps. First, it is important to identify the problem by analyzing the symptoms and gathering data. This can be done using tools such as debuggers, loggers, and trace tools. Once the problem has been identified, the next step is to isolate the problem by narrowing down the possible causes. This can be done by using breakpoint, stack analysis, and other debugging techniques. Once the problem has been isolated, it can be fixed by modifying the code or configuration settings. Finally, the fix should be tested to ensure that it solves the problem and does not introduce new issues. So now RTO's use cases. RTO is widely used in various industries such as automotive, aerospace, medical devices, and consumer electronics. One of the most common application of RTOs is automotive system, where it is used to control various functions like engine management, transmission control, and safety features. RTOs is also used in aerospace systems to control flight systems and navigation. In medical devices, RTOs is used to monitor vital signs and control drug delivery systems. In consumer electronics, RTOs is used in smartphones, smartwatches, and other wearable devices to provide real-time processing and multitasking capabilities. Another important application of RTOs is in industrial automation, where it is used to control manufacturing process and machinery. RTOs is also used in robotics to control the movement and actions of robots. In addition, RTOs is used in telecommunications system to manage network traffic and ensure reliable communication. Finally, RTOs is used in military and defense systems to control weapons, surveillance systems, and other critical functions. So now RTO's limitations. While RTOs offers many benefits for embedded system design, it is important to also consider its limitations. One key limitation is the potential for increased complexity and overhead. Because RTOs requires more resources and management than traditional embedded system, it can be more difficult to implement and maintain. Another limitation of RTO is its real-time performance. While RTOs is designed to prioritize the task and ensure timely execution, there may still be some latency or delay in processing. This can be a concern for application where timing is critical, such as in medical devices or aerospace systems. So finally we come to the conclusion. In conclusion, we have learned about the importance of RTOs in embedded system design and how it compares to traditional design. We have explored the architecture, task management, scheduling algorithm, synchronization mechanism, memory management, debugging and testing, use cases, and limitations of RTOs. RTOs offers a powerful toolset for designing efficient and reliable embedded system. By following best practices and understanding its limitations, we can take full advantage of its capabilities. As the demand for smarter and more connected devices grows, RTOs will continue to play a critical role in shaping the future of embedded systems. Thank you.